Hello, and welcome to the first segment of our video book, How Small Is It?, where we'll examine the size of things, from where we see them around us, everyday things, down to the smallest things that exist. For that, we'll be using a meter stick. A meter is roughly the same size as a yard. It's just 3 inches longer. In addition to how much space an object might take up, we're going to be looking at how little its mass and energy might be. For that, take a look at the apple. 100 grams, roughly. And to raise a 100-gram apple, 1 meter, is the energy of 1 joule. We'll get much smaller than that as we move into additional segments. We see things because light bounces off an object and into our eye. But the smaller things get, the harder they are to see. A human hair is about 1/10 of a millimeter. That's a millimeter is a thousandth of a meter. In order to see things this small or smaller, we use lenses, like this lens here, to get a better look at the size of a hair. But how far can we go bending light? And just how small can things get? We'll be using microscopes, various kinds of microscopes, to see down to the nanometer level. A nanometer is 1/billionth of a meter. There are 25,400,000 nanometers in an inch. So let's get started with optical microscopes. Magnifying tools use lens combinations to bend light at an angle to increase the size of the image that's sent to the eye. The light traces the light rays back to a virtual image larger than the actual object. The more we bend the light, the larger the image appears. We use X after the number to represent the expansion factor of a microscopic image. For example, the magnifying glass we used in my backyard can double the size of an image, so it would be designated 2x. Therefore, if we divide the apparent size of the image by the magnifying power of the lens, we get the object's actual size. Evidence points to the first microscope appearing in the Netherlands in the late 1500s. We know that Galileo used them in the early 17th century. The discovery of things like blood cells and microorganisms in the late 1600s really accelerated interest and development. There are a wide variety of optical microscopes, but they all have 3 basic parts: a quality light source with focusing capabilities, a focal plane for the specimen, and key magnifying lenses called the objective and the eyepiece. Let's take a look at a few things we can see with the optical microscope. Thanks to Greg A. Smith, we have a fantastic microscopic look at what's in a backyard. With standard microscopes, we can see things as small as 0.2 micrometers. That's 0.2 millionths of a meter. Along with factors such as lens size and quality. The limit is hardwired due to a light effect called diffraction. Diffraction of light occurs when a light wave passes over a corner or through an opening or slit that is approximately the size of the light's wavelength. We see this in daily life all the time. For example, diffraction through clouds causes this common yet beautiful sight. A very simple demonstration of diffraction can be conducted by holding your hand in front of a light source. As your face approaches your fingers, you begin to see a series of dark lines parallel to the fingers. The parallel lines are actually diffraction patterns. To understand how this works, we need to take a look at the difference between particles and waves. Particles are localized and bounce off each other. An important aspect of collisions between particles like these is that the momentum of the system is the same before and after the collision. Momentum is the mass times the velocity. In nature, this quantity is conserved. We'll use this law of nature later on when we start colliding particles to see what happens. Waves, on the other hand, are spread out and pass right through each other. When they move through each other, they interfere with each other. They can even interfere with themselves, creating interesting patterns. Newton thought light was a particle because he never witnessed light diffraction. The wavelength of light was too small for the experiments he ran. For decades, his view was never questioned. But in the early 1800s, that changed, based on experiments by Thomas Young. Here we see light traveling through two slits and then interfering with itself on the other side. A diffraction pattern is etched onto the back screen. This is the famous double-slit experiment. When Thomas Young did this double-slit experiment, he showed conclusively that light diffracted and therefore was a wave. Here's his sketch of two-slit diffraction that he presented to the Royal Society in England in 1803. Because of diffraction, instead of seeing points, each point is spread out into a disk called an airy disk. The resolving power of any optical instrument is its ability to produce separate images for two adjacent points. This resolving power of optical microscopes is about 0.2 micrometers. The bottom line is that you can't see a thing that is smaller than the wavelength of the light used to illuminate it. If we're going to do better than 0.2 micrometers, we'll need to use something else to do the illuminating. And for that, we'll need to get a better handle on the nature of waves and particles. Until the 1900s, based on Young's results, it was understood that light was a wave. And because waves were known to need a medium to propagate through, like water waves, it was assumed that all space was filled with a massless substance that was given the name ether. Then, in the mid-1800s, James Maxwell, who was studying electricity and magnetism, proposed that the existence of an electric charge filled empty space with an electric field. Here's a NASA picture of small threads suspended in an oil aligned with the electric field of a charge. Accelerating the charge causes the electric field to change. Furthermore, he showed that a changing electric field created a magnetic field, and a changing magnetic field created an electric field. So the accelerated electron creates a disturbance in the electric field that propagates itself through space as an electromagnetic wave. Earlier, Michael Faraday and André Ampère had measured the resistance of empty space to the forming of electric fields called permittivity, and the resistance of empty space to the forming of magnetic fields called permeability. Using these numbers, Maxwell calculated the speed of his wave and found that it was exactly the speed of light. He had discovered that light is an electromagnetic wave. There's one more thing to point out about electromagnetic waves that will become important as we move inside atoms in the next segment. Mathematically, waves can be described by a generalized wave equation that describes a vast number of different kinds of waves. For waves like this one, the solution to the wave equation provides valuable information about the wave's characteristics, including its amplitude at any point in time. The idea of an ether filling otherwise empty space was rendered unneeded for light propagation once electromagnetic radiation was understood. So it faded from our vocabulary, replaced by the idea that empty space supported magnetic and electric fields, and light represented a disturbance in the electric field. The exact characteristics of so-called empty space will be a recurring subject for us as we approach our segment on the Higgs boson. You'll recall from our segment on distant stars that we can determine temperature from color because of our knowledge of black-body radiation. You'll notice on this graph that as the frequency of the light moves into the higher frequency ultraviolet range, the spectral energy goes down. But the classical formula for radiation energy has it increasing to infinity when the frequency goes up. This dramatic inconsistency between the theory and observation became known as the ultraviolet catastrophe. It wasn't until the early 20th century that Albert Einstein and Max Planck solved this problem. In 1900, Planck came up with a solution for black-body radiation that fit the observations. But he had to assume that the light emitted was discontinuous instead of continuous, as universally assumed at the time. Furthermore, he calculated that the light's energy was dependent on the light frequency and described by the simple formula energy is equal to a constant times the frequency. The constant became known as Planck's constant. With this assumption, he generated equations that exactly matched the black-body radiation observations. Unlike the speed of light, that's a really big number, Planck's constant is a really small number. Remember that a joule of energy was the energy needed to lift the apple? Planck's constant is 66 billion trillion times smaller than that. That's why we don't see the effects in everyday life. 5 years after Planck published his light is created in quantized chunks of energy theory, Albert Einstein demonstrated that light was consumed in quantized chunks of energy as well. This was done using the photoelectric effect. The photoelectric effect is the ability of high-frequency light to dislodge electrons from a metal surface. In this experiment, a vacuum tube contains two plates connected to an external circuit that produces a voltage between the plates. A light source shines on one of the plates. If an electron is dislodged from the metal plate with enough energy to overcome the voltage, it will reach the other plate. This is measured as an electric current. As the voltage is increased, the number of electrons that can make it across goes down. At some point, the voltage is large enough to prevent any electrons from making it across, and the current stops. We can measure and graph this effect for varying light frequencies. Here's what we see. Being a straight line, we can measure the slope. We get energy is equal to a constant times the frequency, and the constant came out to be exactly the same as what Planck had come up with when he studied black-body radiation. So, Light starts out quantized, as demonstrated by blackbody radiation, and is absorbed quantized, as demonstrated by the photoelectric effect. So it stood to reason that it travels quantized as well. In other words, it's a particle, not a wave. But what about the earlier proof that light was a wave? For that, we revisit the Young double-slit experiment. We've seen Young's diffraction pattern that told us light was a wave. So now let's fire photon particles one at a time at the slits. What happens is that for each photon, the detector registers a hit on the back screen at a single point. And at first, with a small sample, the hits seem random. But over time, we see that the interference pattern re-emerges. Here's a video of the detector plate. It's as if each photon was contributing to the interference pattern, even though there wasn't another photon to interfere with. So, the conclusion is that photons interfere with themselves. Turns out that they only interfere with themselves. They never interfere with another photon. Now look what happens if we detect which slit the photon went through. Here, a detector registers yes if the photon went through the upper slit, and no if it didn't. The detector sees a photon coming through the top slit around half the time. We assume that if a photon went through one of the slits and it was not the top slit, then it must have gone through the bottom slit. Here's the resulting pattern. But this is the pattern for particles. If we turn off the detector, we get the pattern for waves again. This duality puzzled scientists for years and is argued about to this day. A good way to look at it is light propagating through space as a wave, but at any time it interacts with something, it interacts as a particle. In other words, it is created as a particle and absorbed as a particle, but travels through space as a wave. In 1924, Louis de Broglie predicted that this wave-particle duality will work the same for particles like electrons and atoms. By 1927, this had been demonstrated for electrons and atoms. With today's equipment, we can even see it for large 20-atom carbon molecules. So we have light waves acting as particles and particles acting like waves. We call it particle-wave duality, and it is a fundamental aspect of quantum mechanics, and these were the experiments that started it all. So once we understood that electrons travel as waves, they will have a wavelength. Here's the simple derivation conducted by de Broglie. The momentum for light is Planck's constant divided by the wavelength. So the wavelength is equal to Planck's constant divided by the momentum. And we know that for particles, momentum is equal to its mass times its velocity. So a simple substitution gives us the wavelength for the particle as Planck's constant divided by the mass times the velocity of the particle. And if that wavelength is a lot smaller than a photon's, it will enable us to break through the diffusion limit and see things much smaller than a microscope can. So let's take a closer look at this subatomic particle and find out what its wavelength is. In the early 1800s, most people thought that the atom, the most fundamental unit of matter, was indivisible. Also, a lot was known about electricity, but no one knew what was carrying the electric current. For example, highly charged cathode rays were produced inside vacuum tubes in the mid-1800s. But it wasn't until the late 1800s that anyone figured out what was carrying the charge. In 1897, J.J. Thomson used a mass spectrometer to measure the mass of cathode rays. Here's how it works. From Newton, we know that force equals mass times acceleration. So mass equals force divided by acceleration. Acceleration is a change in an object's speed or a change in its direction. If we exert an exact amount of force on a particle and carefully measure its acceleration, we'll know its mass. So we fix the particle velocity with an electric field, measure the radius of the resulting curve as it moves through a magnetic field, and use the basic electric, magnetic, and centripetal force equations to calculate mass. Thomson showed that the rays were made of particles that were around 9.11 times 10 to the minus 28 grams. That's 1,800 times lighter than the lightest atom, hydrogen, that had also been measured with mass spectrometers. Therefore, the particles were not atoms. He had discovered a new particle that was later named the electron. Now that we know the mass of the electron, we can accelerate it to, say, 70% of the speed of light and calculate its wavelength. Adjusting for the length contraction due to relativistic effects, we get a wavelength of 0.0025 nanometers. That's 200,000 times smaller than the wavelength of green light. So let's use electrons instead of light in our microscopes. The most common electron microscope is called a scanning electron microscope, or SEM. An SEM scans the object with a high-energy electron beam, which reflects and scatters electrons, providing information about the specimen's surface structure. Glass lenses are used in an optical microscope to bend and focus the light. Electron microscopes use powerful magnetic and electric field generators, like this one, to bend and focus the electron beam. Here's an interesting look at bees through an electron microscope magnified 150 times. As you'll see, the resolving power of the electron microscope provides images with dramatic clarity and detail not possible with optical tools. Because it's not light, there is no color associated with the images. Color can be added after the image is created by the electron microscope. Here's what a sheet of paper looks like at 1,000 magnification. Here's a human hair magnified 1,200 times. This is a micrograph of red blood cells clumped together with fibrin to form a blood clot. This colored SEM monograph shows the rods and cones in the retina of the eye. The rods are tan and measure around 1 micrometer in diameter. The cones are green and measure around 8 micrometers in diameter. A nerve fiber is a thread-like extension to a nerve cell. Here's a colored scanning electron micrograph of myelinated nerve fibers. The myelin sheath is gray, the nerve inside is pink, and the connective tissue is yellow. Here's the texture of the skin of a spider magnified 12,000 times. The most powerful electron microscopes can resolve images as small as carbon atoms. Here's a sheet of carbon atoms with each atom around 0.14 nanometers in diameter. That's around 1 billion times smaller than the human hair we saw earlier. Given the electron wavelength, this is about as good as we can do. In this segment, we've gone from what we can see with the human eye to what we can see with optical microscopes to what we can see with electron microscopes. In our next segment, we'll take a closer look at atoms and their subatomic particles.